Okay, last time we started talking about the processes and threads. We said that processes are the most basic abstraction concepts of operating systems. If you have an operating system, you cannot do much without introducing a process concept in your operating system. We talked about this, and later we talked about how we create new processes, and then we talked about how we end a running process, and then we said that for some systems there are process hierarchies, for some others there are no. For example, in Unix, there is always one initial process, that's init, okay? That is the parent of all the processes in a Unix environment, in a Unix operating system. And all the processes, what is the only way to create a new process in Unix? It is fork, right? So that init process uses that fork system call to make other processes, and other processes make their own child process, and it continues that way. And this forms a proper hierarchy. In Windows, there are no hierarchies. Of course, there is this parentship and ancestor-descendant relationship in Windows. If I create a new process, that becomes my child, but that's not permanent. I can take, for example, I can take my children and I tell some other processes, okay, these children are your children from now on. So that parentship and children can be transferred from one process to other processes. So that's why we say that in Windows, we don't have the process hierarchy. That's what we said last time. And process states, we talked about it. These were the three main process states. A process could be either running, ready, or blocked. Okay. Well, I mean, if you do a more fine-grained classification, there could be more states. I mean, there is block states and there are sub-states of this block state, but we are not going to look at it. And we said that for the running, it is actually using the CPU. There is always a process running in my computer system all the time. Somebody is using the CPU. It is either my user process or the operating system or the interrupt handler or something else, okay? So somebody is using the CPU all the time. If I have a single CPU, that means that at most one process can use the CPU. If the other processes are ready to use the CPU, they are in the ready state. They are runnable. They are not running, but they are runnable. For some reason, they are waiting. Okay, they are waiting. They are ready. They are waiting. Why they are waiting? Because if there are more than one process is ready to run, only one of them can run. That's why the rest of them are waiting in the ready queue. Okay, usually there is a queue, and in the blocked queue, some processes are not ready to run. Why? Because they are waiting for maybe some input-output operation. Maybe they are waiting for something else to happen. For example, they are waiting for some message. Okay, they say that I send a message to the network and I'm waiting the answer. I am waiting for the answer. So they are waiting. This was the figure. Okay, this figure is from the book. I am either in running state or blocked or ready state. And as you see, from running to ready, there are two arrows. I can go from running to ready or ready to running. From running to ready, what is the event that takes me from running to ready? So how does this two happen? A timer interrupt, right? A timer comes in, okay? Timer comes in and says that, okay, you have run this much. Now I'm going to interrupt you and operating system will take over. Okay, operating system will take over. It will do some things and you will be in the ready queue. You are ready to run, I know, but I need to do this. So if there is an interrupt, that may put me in the ready queue. But as soon as that interrupt is handled, maybe I will be running again. So from ready to ready to running, I can do this scheduling decision from the operating system. From block to ready. So how does this for work? When does this step number 4 happen?
External event completed.
Due to some external event, operating system has completed some job, for example, an IO operation. So, and I was waiting as a process, I was waiting for that IO operation to complete. And that thing is completed. Now operating system says that I completed this operation. So somebody was waiting for it. So I will put that process to the ready state. Not directly running, but ready state. Yes?
So these blocks processes are not directly running in the system.
They are not running. No. I mean, running means that it is using the CPU. Running means that its instructions are being executed by the CPU. Blocked processes or ready processes are not using the CPU at all. Okay, their instructions are not being executed by the CPU.
Can we say, for example, blocked is some kind of driver that needs to be, when we plug the USB stick,
Yes.
USB stick creates a signal to handle, create some job. It's blocked, right?
When you insert a USB stick to the USB slot, it creates an interrupt. That interrupts the running process.
Okay.
Whatever is running is put into this ready queue. Okay. But if somebody is waiting for that USB stick to be inserted, that process becomes, instead of blocked, it becomes ready. Okay. So operating system knows that that process is waiting for this to happen. It happened now. That process is ready to run now. Did I answer your question?
Yes.
Okay. But it doesn't have to be a USB stick. I mean, USB stick is not a very good example. A good example would be somebody's waiting for a keyboard. For example, think about this code in C++. When you say, let's say this is an integer. Okay. When you say this is an integer, okay. When you say I executed this line, now my process is blocked. Why? Because I am waiting for something to happen from keyboard, from standard input. It will be blocked until I get whatever I want. Okay. So I am not going to use the CPU while I am waiting for this to happen. I am not going to use it. As a process, I am not going to use the CPU. I will wait until that data is ready. Okay. I will be in the block state, so I won't be wasting any CPU time. But yes?
Is this ready queue is write queue or basic queue?
Ready queue, well, I think you are asking, is this a first in, first out queue? Is that kind of, that's a scheduling decision actually. I mean, let's say in my queue, well, this is not a perfectly first in, first out queue or last in, first out queue kind of that. Okay, it's kind of a place. This is my queue. Let's say this is my process number 1, process number 2, process number 3 are waiting their turn. Okay, they are all ready. It is up to the operating system scheduler to choose which one goes first. Okay, so it may depend on their priorities. If P1 has a higher priority than the other ones, then operating system says that, okay, you're going to run. Depends on your scheduling algorithm, and we are going to have a whole subsection in this chapter number 2, a whole subsection that will talk about our scheduling decisions. Okay, some of the schedulers say that I will run a process that will take shortest amount of time to complete. Okay, run the short one first. Why? Because if I run the short ones first, that means that my throughput will be higher. Why? Because I am completing more number of processes given a second, right? Some other scheduling algorithm says that I will run the more interactive processes first because they need the interaction, they need the speed. Otherwise, the users will not be happy. Okay, so those are all scheduling decisions, and the scheduling word is a very big word, and we will have a look at it. So this queue, that was a good question. This queue is not a regular first in, first out queue, but if you do it that way, that is called round robin scheduling. It's a first in, first out. So I do it as first P1, then P2, then P3, then I return back to the P1 again. Okay. Okay, so the same, I mean, definitely blocked is not a queue because, I mean, there is no order. Whoever is not blocked anymore, they will be put into the ready queue. Okay, they will be put into the ready queue. Okay. Sometimes the scheduler says that this process has been waiting for so long. Maybe I should run this first. So, I mean, time is a very good, the time, how long ago you started is a good criteria for which one to run first, scheduling decision. Priority is another one. Interactivity is another one. The amount of the duration that they are going to use the CPU is another one. We are going to look at each of those one by one when we look at the scheduling. Okay, good. Yes.
When we are running process on terminal, then we hit a control and Z. Is this the process goes into block stage?
When you hit Control Z, that means that you are trying to suspend your process. Who takes Control Z? Of course, operating system takes it. Why? Because when you hit Control Z, it creates a interrupt, right? That interrupt will be taken by the operating system, and operating system says that while I am running this process on the terminal, somebody hit Control Z. That means that that person is trying to send a suspend signal to that process, and it says that, okay, that process, if you are running, I am sending you this suspend signal, and that process has to handle that suspend signal. There is a way to handle it, and whatever the decision of that process is, it is either suspended or, I mean, you can always override this behavior. You don't have to suspend your process when you get the Control Z. Okay, it is up to you. As a programmer, you may change it. Read about signals. Are they covering signals in systems programming?
Yes.
Okay, so Unix. Okay, Unix kill signal. Maybe I think there was a very good documentation that maybe it was Linux signals. I was going to show you some. I think it is this. No, yeah, maybe this one. These are the signals. Okay. These. Oh yeah, this is where I got. See, this picture I have stolen from this web page, and these are the. Oh, these are the status. Remember yesterday when I said the status of my processes. One of them was as sleeping. Okay, I said suspended. The other one is R. There is a status code named D, uninterruptible sleep, waiting. Uninterruptible sleep. I don't know what that means. Why would I interrupt the sleep? Okay. Do they talk about zombie processes in Unix, in systems programming? Zombie processes. Zombie means.
If you kill its parent and the child process is still living, it is a zombie process.
If you kill a parent, if the child lives, usually when you kill a parent, all the children has to be killed too. But for some reasons, due to resource sharing and that kind of stuff, sometimes you cannot kill the children, so they become zombies. Okay, so they talk about this kind of stuff. Okay, these are all specific to Unix and Linux. You don't have anything exactly that corresponds to these kind of status in Windows or some other operating system. What?
When parent died, init process adopted the child process?
Yeah, when in Unix, when the parent dies, all the children has to die.
So where is the time that init adopted the children?
In Unix, there is no adaptation. Yeah, I mean, your parents are fixed. You cannot change your parents like real life, and you are stuck with your parents.
You said that
In Windows, you could. Yeah, in Windows, the parentship, okay, as an ancestor descendanship can be changed if you have the enough permission. In Unix, it is not. That's why we say that there are no process hierarchy in Windows. But I was going to show you the signals. I was going to show you a signal. Yeah, this is a exec function system call. Signals, where are the signals? I was going to show you, maybe just, yeah, main PID, not that one. So many signals are there. Maybe at the end. Yeah, these are the signals. And I think there was one nice example, very small example. Yeah, okay. Okay. It's a very simple C code. Can you see it? Do you see it? Yeah. Okay. Very simple C code. It says that I have my main and I have my interrupt signal handler. Control C. Control C. Okay. So at the beginning, I say that I am registering this function as a function to handle the SIGINT, this control C signal. Okay. And I am just doing this. I am just going into an infinite loop. Just sleep 1 second, and I am blocking myself. I block myself for 1 second, and after a while, okay, this is a very good example. When I block myself for 1 second, I am waiting something to happen. What I am waiting for? I am waiting for that 1 second to finish up, and after that I start again, and I say I am waiting for interruption. I am waiting for somebody to hit the Control C button actually. When they hit the Control C button, this function is called because I am handling it. I say that, okay, I got the signal, and then what am I going to do? I am going to make my SIGINT the default SIGINT signal. Okay, so after that, whatever the default is going to be done. Probably my program is going to be killed. Okay, this is how the signals work. This is how the signals work. When you say Control Z or Control C, that's a signal to my program. And if your process is a Unix process, your program has to know how to handle those signals. Okay, we don't write them because by default there are handlers of those signals, like the Control Z signal or Control C signal. Okay, if you like to override them, this is how you do it. Read this page. Okay, very nice. Okay. Linux processes and signals. A very nice explanation. As I said before, there is no way that I can tell you everything about the Unix environment, Windows environment. Either we don't have enough time to cover them in these kind of classes, or I don't know anything about them, or nobody knows anything about them. You need to figure them out, okay? Not everything that you need to know are supposed to be learned in the class. Yes.
In this example, there is a void test. Void test in this example.
You mean at the end? Yeah.
What's the meaning?
Well, that's a C question. I don't know what I don't. Okay, I don't know the answer, but I can make up something immediately. Just you know the rules, right? Which one? So I am calling the signal. This is the same thing. I don't know why they put this void in it. I think there might be more than one just to disambiguate the call. I don't know.
Actually returns sig handler or something like that. Because they casted the void.
So what do you do with the return signal, return value? What do you do with the?
You don't have to deal with it actually.
But why am I casting to it? It looks like it is trying to disambiguate something, but disambiguation by looking at the return thing is not a good thing. I don't know. Let me see. Does it say anything about that? Why we? I don't know. I don't know why they did it. Just look it up. Try to find it and tell me why they are doing it. Okay, let's go back to our slides again. That small program, it is most of the time in the block state. it is running very short amount of time. It just keeps running. As soon as it runs, it goes to that loop, and that loop goes to sleep again. It doesn't do anything. So maybe 99.99999% of the time of that program is in the block state, okay? Because it is running a very small amount of code until somebody hits that Control C. The first time you do the Control C, it changes the signal back to the original. Second time you hit the Control C, your program is terminated. Okay, that was your question. I hope I answered your question. Any other questions? Okay, then maybe I will continue. So we talked about the process states, and let's say these are my processes. I have n processes from process number 0 to n minus 1, and logically they sit on top of a scheduler. Scheduler makes a decision to run a ready process out of all of the available processes. And it is task of the scheduler to make all of these scheduling decisions. And scheduler is maybe the most important part of the operating system. It is not much code. It is usually written with a heavy assembly proportion. Okay, most of the scheduler code is in the assembly, and it has to be very fast, right? Because every time you make a switch, you have to go to the scheduler. And it is so important, it has to be in kernel mode. Otherwise, you cannot do this switching. I mean, what does the scheduler do? It changes the most important registers of the CPU. And we didn't see it yet, but it changes the page table entries related to the memory management and etc. So it has to be in the privileged mode. That's why even for the microkernel operating systems, it has to be in the kernel area. Okay, that's the lowest part of the operating system. Of all the layered operating systems that we looked at, if you paid any attention, scheduler was at the bottom. Okay, because scheduler is the part of the operating system that is responsible for making multi-programming possible. Okay, good. Questions so far? And not this homework, but in the next homework number 2, you're going to write your own scheduler. And for that, you need to figure out how to save. When you switch from one process to another process, you need to figure out ways of how to save all that information about the process, like the registers, like the stack registers and the program counter, program status words, and all the other registers, everything. Okay? You need to come up with a page table structure of your own. Okay? So let's talk about this page table. Okay? In the kernel area of the operating system, with the scheduler, there is an important data structure. It is called process table. Process table. Okay. And that process table contains many entries. Each entry is for a process. And that process table contains information about the processes, such as processes state. What do I mean by state? Is it blocked? Is it ready? Is it running? Okay. So that state is in the table. What else? The program counter of the process, if it is in the blocked or ready state, stack pointer, and memory allocation, how much memory it is using, etc., that kind of stuff. The status of the open files. What do I mean by the status of the open files? How many files do I have open? And what are they pointing to? And if the file is open, I need to have a position inside the file, right? The seek position, that kind of information. Accounting and scheduling information. What do I mean by this? Accounting and scheduling information. Where is it? Yeah, wow, didn't work. While I am trying to, what happened now? Okay, while I am trying to, okay, accounting and scheduling information. It says that you need to keep this accounting and scheduling information in the process table. For each process, I keep this. What is accounting? Muhasebe in Turkish. I mean, the processes, they don't use money. They use what? They use CPU time, right? So it's an important knowledge to know how much CPU I have used as a process. If I use it too much, and if the other processes didn't get their fair share, then maybe as a fair scheduler, I should let the other processes use the CPU instead of this process. So accounting is important. Scheduling information, how do I schedule this? I mean, when was the last time this process had worked, had used the CPU, right? Those are all important information. I need to keep them somewhere. And everything else about the process that must be saved, okay, when I switch from one process to other process. If I had a single process on my computer, okay, I don't have to save anything because I have a single process, okay, and it is running, and I know that it's not going to be switched from one place to another place. So what am I going to do? I don't need to do anything. It uses the CPU, all the resources. But if you have more than one process, then you need to have a process table or at least a place to save your data. Okay. So in your first homework, maybe you are going to write a very primitive version of your process table. Well, yours is not going to be process table maybe because you will have at most one process running other than the operating system, right? It's going to be a very, very primitive version of the process table. Maybe a single entry, yes?
And maybe you have to store the OS situation on the table.
Yeah, well, maybe, I mean, you might think that OS is one process and the other one is another process. Yeah, maybe two processes. But one of them is running all the time. So maybe you need just one slot. So it is your decision. It is your design decision of your operating system. Okay, good. So as I said before, process table is a table that's kept by the operating system. Of course, it should be in the privileged section of the operating system memory area. Nobody should be able to access it. Nobody should be able to modify it other than the operating system, right? I mean, if you can access the other processes, process table entries, maybe you can just turn down their priorities and always let your process use the CPU all the time, which would not be a good thing, right? Which would not be a good thing. So it's a privileged table. It's a privileged location in the memory. It's part of the kernel. It's part of the operating system. Good. And these are the things that are saved, typical things. These are not the complete list because the complete list depends on the operating system. That are saved in the process table for each process. For each process, I save these. For the process management side, I keep my register, all of my registers, tens of them, including my program counter, program status word, stack pointer, etc. Okay, these are already registers. Okay, these are already registers. But other than these, I have other registers too. Process state, as I said before. I mean, am I running? Am I blocked, etc. I keep using this program PS. What does PS stand for? PS? Process status. Process what? Report a snapshot of the current processes. Process snapshot. So PS is a program that goes to the process table and makes a nice report about the process table, right? It says that when I say PS or with the options like EF, AX, yeah, okay. It says that you have in your process table, you have 4 processes, okay? And these are the status of those processes, okay? These are the state. And how much time you used, it is here. And what command you use, okay, what is the image of your process, okay? On the desk, it is this one. And these are the command line options that I have used to start these processes. I think I can get even more information. I don't know, is there anything like long information? Yeah, okay. User ID, process ID, PPID. See, these are priorities. This is a priority. What is this? VSZ, I don't know. Memory related stuff maybe? How about this one? Top is another one. Top is it keeps updating my table. Okay. So I say that you have 4 of them, and these are the whole story. It looks like, I think this is virtual memory size. I'm just making up. How much CPU you are using? How much memory are you using? That kind of stuff. What did I do last time? LS. Where is my LS? Did I keep my? Yeah. Okay. Here it is. Okay. While LS is running, let me run top. Oh, okay. So LS is using 16% of my CPU time now. Memory, it doesn't take much memory. PID is there. Priorities are the same. Okay. So both PS and top, they just check your process table in the kernel area, and they report information about this to you. Okay. Good. So how PS or top, they are user programs, right? How come they can have access to the process table, which is a privileged information? How come they can get that information? They do system call. It looks like you can read all that information, but you cannot change that, right? You cannot change that. Also, Unix has some tricks about them. I mean, you as a system administrator, I can give privileged access to some of my programs like PS or top. Okay, it is possible. You may say that this program is going to run, and this program is privileged. It can override the other users' priorities, and it can do whatever they want. Okay, and these are the priorities. Do you know how to lower the priority of a process? Do you know how to lower a priority of a process in Unix? This is what you do. You say that I am nice. I am going to lower my process's priority. There is no unnice or anti-nice. You have to be nice all the time. You cannot increase your priority, but to be nice, you can elect to lower your priority. See, this one, priority is 10. In Unix, lower the number, lower the priority. Or just the opposite. I don't know. I mean, this is not, as you know, this is not exactly Unix. I think it is just the opposite. This is Windows priorities, maybe. Okay, good. So, I mean, these are not Unix processes. These are Windows processes. Okay. Oh, okay. So it is doing something. I don't know. Okay, let's go back. So if you run PS or top, their job is to just look at this process table and report that information to you. And the process state is taken from that table and printed out. Priority again, you there. Scheduling parameters, you have seen that, right? There was this time thing, right? It says how much time this process had used. I had it. Process ID, parent process, process group, signals, okay? What kind of signals they are taking and addressing. They are all there. Time when process started is important. CPU time used again. Children's CPU time. Time of next alarm. These are all process management related stuff that is put into the process table. These are the information about the memory management. Where is my code, text segment of my program? Where is my data? Where is my stack? Again, for the file management, we have these. Okay, as I said before, this is not a complete list. This is just to give you an idea, what kind of things we keep in those process tables. And size of the process table is very big. How big? In my small computer here, as I showed you before, I have more than 100 processes running, so it is large. It is very large. Okay, for that small boxed environment, Unix environment, it is not big, but the real Windows processes are. Let's do an experiment. Let's do this experiment again. Let's make this nice and. Oh, how do you lower your priority even more? You do this, nice. What is nice? Nice is a utility, right? As a command line parameter, it takes another command. Okay, so when I say be nice and run this for me, this one says that be nice and run this for me, but the thing that is running is another nice. So let me do this nice thing, and let's write top. So these are all. I guess this is all the lowest that you can go, 1. I am trying to see if I can see these processes in my Windows. Okay. There is this Ubuntu thing is running, and yeah, okay. Console window, Microsoft subsystem. I think it hides them all. I think it is running some hidden threads there. I don't know. I couldn't see it. Is there any way to list all the processes? I mean, not the active ones, but all of them. I think it is in the view. Expand all, collapse all.
Right now.
What? Yeah, okay, here it is. Oh, okay, so so that ls is not actually a Unix process, it's a Windows process. I have 2 of them. Both of them are Windows processes, but that small box is virtualizing everything. It is showing me it as a Unix process. So it is using lots of memory too, right? So I have 2 of them. And my shell, maybe bash. Bash is. Let me try to. Okay. Where is bash? Do you see bash? Oh, okay. The bash is here. So Windows definitely knows about them. Windows is managing all of my processes, not Unix. Well, as I said, I don't have any real Unix operating system there. And probably those priorities are Windows priorities, not Unix priorities. Because as I know, higher the number, more priority the process has with the Unix, but just the opposite in Windows. Okay, good. Okay, power usage? Oh, okay. Let's go back, and let's go back one more. And if I don't have any questions, let me continue with this. Okay, this is a very important piece of information. This is what happens when I get a interrupt while a process is running. Okay, so these 8 steps. Some of them are handled by the hardware, which has nothing to do with the operating system. It is completely different. I think first 2 steps are done by the hardware. Also, the last step 8, number 8, is done by the hardware, and you learned about these. In the last semester with your organization course 331. The rest we are learning it. Okay. So when I when I am running as a process, I am using the CPU. I am receiving the CPU. A hardware interrupt has happened. Let's say this driver says that the data is ready. Okay. The data is ready. So when the interrupt happens, from the interrupt controller, CPU gets a signal, and it tells the CPU, stop whatever you are doing. Okay. So what are you going to do? The hardware saves the program counter, the PC. Remember, the program counter shows me where my current instruction is that I am executing. Then I save program status word. Okay, PSW, which is very important. It keeps my mode of operation, kernel mode or the user mode, and my carry flags, my branching flags, and etc. That one is saved too. So 1, 2 most important things. It doesn't save all the registers. It just saves the most important ones. Okay, when the interrupt happens. We don't want to save all of them because all of the registers, if I like to save all of them, for some systems, 64-bit systems, there are more than 50 registers to save. I don't want to spend that amount of time or that amount of memory for all the interrupts that happens. Okay, this is done by the hardware. Operating system doesn't know anything. Okay, the program was running, interrupt came in. Okay, that interrupt caused the hardware to save the program counter and the program status word. Okay, and then hardware again says that an interrupt happened. So who is going to handle this interrupt? I need to find this interrupt from the interrupt table. So it goes to the interrupt vector, and the interrupt controller says that interrupt number 7 has happened, which turns out to be the disk interrupt. So it picks the interrupt vector number 7, and it finds the address of the interrupt handler, and it says that, okay, I saved the program's program counter and the program status word. Now I know which interrupt handler to run. I am going to jump to that location and I'm going to run it. That's what the hardware does, number 1 and number 2. That interrupt handler is written by the operating system. Now operating system starts running. Okay, so it is the job of the hardware to make all these saves, find which interrupt vector, which interrupt to handle the already reported interrupt, and then now I am going to handle that interrupt using this assembly language procedure. That assembly language procedure, as soon as it starts for most operating system, it saves all the rest of the registers. Okay, remember I had sometimes more than 50 registers. I am saving all of those registers. Okay, and then where do I save those all the registers, by the way? When I say save the registers?
Memory.
That's a good thing. What memory? No, but if I save them on the stack, so where am I going to find it later? Whose data is that? Whose data are those registers? That processes. So where should I put that? Where should I put that information? In the process table, of course, because the process table has a place to save all that data. Okay, so this assembly language procedure saves all the registers into the process table for the current process. All the temporary values are saved. So after this point, I know that after I am done with this interrupt, I can restore everything. I can go on with whatever I was doing with the process number 1, for example. Okay, so number 3 is done by the assembly language. I cannot do this with a C code because C code doesn't know how to save the contents of a register to some memory location. We don't have any instructions like those. Okay, in C at most, what we can do is just assignment. Okay, we cannot do more than that. You don't want your C code to depend on the processor. You don't want to have instructions in your C program that says that move the content of this register to this memory location. That would be too low level, even for a language like C. So we write this part of the operating system in assembly. Okay. Then assembly language says that, okay, I saved everything. The program is safe now. I can restart that program, that process. So I'm going to set up a new stack of my own, okay, while I'm handling this interrupt. Okay, I set up my new stack, and then I can continue from this one. The rest can be handled by C routine. Okay, number 5, the real interrupt service routine starts running. It says that, okay, number 7 happened. Number 7 is a disk interrupt. So I will start talking to the driver. Okay, driver knows what happens. Okay, it says that, okay, this happened. The driver, what are you gonna do? I need to load this much of data from the driver's memory to the main memory. Okay, I'm going to do that. Okay, after I handle that interrupt, whatever it is. So number 5 is very big actually. Number 5 does lots of stuff, but it is all written in C. And it depends on the type of interrupt happened. Number 1, 2, 3, 4, they are all the same for all kinds of interrupts. They are saving stuff, right? Other than the number that you looked up, okay, from the interrupt vector, everything is the same. Number 5 is different for each different interrupt type. After number 5 is done, so we start going backwards. We start going backwards. We say that, okay, I am done. I need to reschedule one of my processes. So after this one, a process has to be run. And which process am I going to pick? It depends on your scheduler decision. So you ask the scheduler, pick a process for me. You don't have to go back to the process that was interrupted at step number 1. I mean, remember, process was running. I interrupted it. After I handle the interrupt, I don't have to go to that process at all. I can reschedule. I can schedule another process. That's my scheduling decision. Okay, you don't have to say, okay, I am interrupted, but I will take the CPU back again. No, because somebody else can take the CPU. It's a scheduler decision. So the scheduler decides which process to run next, and then after I did that, I return to my assembly code so that I can put all the related data from the process table to the CPU registers, and then control is passed back to the assembly language to load up all the registers and to the one of the processes. Okay. Remember, when we do the system call, there is an instruction in MIPS, right? System call. There is another instruction that's called system return. SYSRET, system return. So you return from a system call or from an interrupt like that, because when you are handling the interrupt, you are in the kernel mode, not in the user mode. Or when you are handling a system call, you are in the kernel mode. When you go back to the process, you need to put the processor back into the user mode. Otherwise, things would be very bad. Okay, memorize all of these 8 steps by heart and try to imagine in your mind what's going on with the interrupts. You already knew, I guess, this part and this part from the organizations course. Okay, the rest is operating system. Without knowing the computer organization, computer hardware, you cannot know what's going on with the operating system. Without knowing what's going on with the operating system, you cannot be a very good computer engineer or even a programmer, right? So these are, hardware stuff is very important. You need to have very good knowledge of the computer organization. You need to have a very good knowledge of the operating systems. Without those, you cannot be a very good software engineer or computer engineer. I mean, I am hearing that many departments are ignoring these kind of courses, like the fundamental logic design courses or the computer architecture courses. They are not doing right. They are doing something very, very bad. I mean, software doesn't mean that it is all code stuff. You need to know about the hardware. Without knowing the hardware, you cannot write efficient programs. You just write programs maybe, but not efficient programs. Okay, any questions so far? Before I take a break, let me take 1 or 2 questions. If you don't ask me a question, I will read the name and I will make them ask the question.
I can ask a question.
Okay.
But it's about the homework.
It's about what?
Homework.
Maybe later during the break. I mean, if it's related to this stuff about homework, yeah, you can ask it. It's only okay. Emre Özgün. Emre, is Emre here? Okay, ask me a question, Emre. It says zorunlu here. Okay, so you need to ask me a question. I don't know what zorunlu means. So what's your question? You didn't have a question? That's not a question. I cannot answer that, no. So what's your question? I need a question, no. I will pick somebody else. I will come back to you. Fatih Selim Yakar. Fatih, where are you? Okay, ask me a question, Fatih. You have what kind of question again? What is your question? I have been talking nonsense. Doesn't this make any sense to you? Okay. Pınar Erdem. Pınar, where are you? Okay, ask me a question.
I don't have a question to now.
Ahmet Ergani.
Here. A question.
Yeah, just
Why can't we get a system where there are only two process states? Why do we really need to separate
what would be the states names?
running and not running? Why do we need to separate the ready and block state?
Because when the scheduler makes a new decision, which process is going to take the CPU, it has to know which processes are ready. Okay? You cannot run a process that is blocked, waiting for something. It cannot run, it is waiting, right? It says that, remember our process that says I'm going to sleep for 1 second. What is the meaning of running that process again? Because it says that I'm going to wait for a second. It is blocked. It is not ready. So you need to have at least 1/3 group says that these processes, they like to run, but they cannot because they are waiting for something to happen. They are waiting, okay? And the others are ready. The scheduler only deals with the ready processes. It doesn't pay any attention to the others. How many processes did I have on my computer? More than 100, right? How many of them are ready, do you think? Maybe 3 or 4 at most. Well, with this multi-cores on my CPU, maybe only one of them is ready. Well, no, that's not true. Most of the time, what is my CPU usage now? 23%. So 70% of the time, scheduler cannot find anybody in the ready queue. Say that it is empty. I'm not going to run anything. So instead of scanning all 200 processes to find the processes to run, it just scans the ready queue and picks one. Okay, that's the simplest answer that I can give you. And the block set is also useful too. Operating system say that if something has happened, somebody in the block list should be waiting for this one. Okay, it just scans the block list. It says, okay, this IO happened and this process was waiting for it. So I will let this know that now you are ready. Okay, that was a good question. Any other questions? Okay, everybody think of some, make up some question. Next lecture, after 10 minutes, I will ask you questions. No, I will ask you to ask me questions. Hayır yok, imza atmıyorum ya. Ne ki buraya geliyorsunuz böyle ya? Yok ya, zamanında gelin imzalayın ya. Ha? Tekrar geri gidin Petr'in öyleyse.
Şimdi böyle oluyor.
Ne yapayım, bana ne? İkinci derse gelenler olur, o zaman bakarız bir daha.
Hocam ödevle ilgili bir soru sorabilir miyim?
Evet.
Şimdi Sharp assembly programı var ya, ondaki komutlar şey mi olacak mesela linear search?
Oradaki komutların sayısı çok fazla değil. Yaptığınız 4 tane program var. Onlardan bir tanesi olacak.
Ha, mesela linear search oradaki komutlardan bir tanesi olacak değil mi? Orada mesela argüman olarak verecek mesela listeyi, öyle mi?
Hangi listeyi?
Aradığımız listeyi linear search için.
Linear search'ün nasıl yapılacağı şeyle ilgilendirmiyor ki. Ben sadece onu çağırıyor.
Yani Sharp o programı çalıştırıyor sadece, yani kendi main'i var.
Size gösterdiğim şeyin aynısıdır.
Nasıl?
Size gösterdiğim shell vardı ya, shell ne yapıyordu? Bana komutu ver ve parametrelerini ver diyordu. Onu çalıştırıyor değil mi?
Evet.
Sizde parametre diye bir şey yok. Linear search çalıştığı zaman nasıl çalışıyor? Siz karar vereceksiniz zaten.
Yani listeyi kendimiz hard codelayacak mıyız aslında?
Bilmiyorum ki. Senin sorduğun shell sorusu değil, linear search sorusu. Değil mi? Linear search nasıl çalışacak diye soruyorsun sen şu anda.
Ödevin mantığını işte tam anlayamadım ondan.
Ödevin mantığı 4
sadece
tane bize assembly kodu yazacaksın. Linear search, binary search, sort,
Selection source
bir de bir şeyler, tamam mı? Onların tam olarak nasıl çalışacağını biz size söylemedik. Ya belki kullanıcıya sorar sayıları gerektiğinde diye. Belki de sabit bir listeden alırlar. Bilmiyorum. Ona siz karar verin.
Tamam.
Shell'e geldiği zaman Shell'in yapacağı tek şey hangi komut çalıştırayım? Linear search. Hangi komut çalıştırayım? Selection sort. Hangi komut çalıştırayım? O.
Tamam.
O.
Hocam bizim Spim Simulator
Shell'de çalıştırabilirsin bu arada. Shell'in içerisinde ama biraz da karışık.
Spim'in içerisinde bizim bunu stack'leri değiştirmemizi, işte process table'ımızı tutabileceğimiz bir sistem var mıdır?
Bir bak kod elinde.
Yani ben baktığımda bulamadım çünkü.
Process table diye bir şey yok. Spin zaten
Evet işte,
bir tane
hiç
emülatör yapılmış.
desteklemiyor.
Birden fazla proses yapılacağını düşünmemiş. Ama bir tane orada bir prosesör var. Tamam mı? Sen prosesörün istediğin değişikliği yapabiliyorsun. Yani değişiklik yapmaktan çok. Yeni instruction ekleme falan filan yok. Çünkü sadece ben bir dosyayı değiştirdim ama prosesörü, o emülatörü çalıştırmak için tüm fonksiyonlar elinde var.
Evet.
Nasıl yükleniyor, memoriyi nasıl kullanıyor falan da fişmandı. Onları istediğin gibi değiştirebilirsin. Yani
bizim-
birazcık üst seviye organizatör gibisin. Bu buraya olsun, bu buraya olsun, bu da bunu yapsın falan gibi şeyler.
Yani bir
söyleyebilirsin.
simülatörü değiştirerek bunu çözmemiz.
Evet, aynen öyle. Simülatörü değil de simülatörün parçaları var. Bunların parçalarını uygun bir şekilde kullanarak. Yoksa simülatörü değiştirmene izin vermeyin. Sadece bir dosyayı değiştirebilirsin.
Syscall sadece.
Evet. Öyle değil mi? Başka değiştirmek yok. Ama diğerlerinin içerisinde istediğini çağırabilirsin onu.
Ama çalışırken mesela Spim Simulator çalışırken onun içinde başka bir şey çalıştıramayız o zaman.
Niye?
Çünkü kendi bir
Çalışırken
şeyi var.
ne kullanıyor? Hangi verileri kullanıyor? Memory'yi kullanıyor.
Evet.
Register'ları kullanıyor.
Evet.
Onları erdem elinde. Onları save edebilirsin değil mi bir kere sen?
Bunu CPP'de mi yapalım? Yani
Nerede yapacaksın başka?
Shell bir assembly dosyası.
Tabii
O
Shell'de
yüzden-
yapamazsın. Tabii ki operating sistem eklenti yapıyorsun. O işletim sisteminin bir görevi.
Tamam.
Onları
okey.
save etmek, tekrar bu bittiği zaman tekrar yerlerine koymak, çalıştırmak.
İşte bunların hepsini ilk yıl yapmış olacağız.
Ha?
Schedule'ı da yapmış olacağız o zaman biz şimdi.
Hayır, scheduler
Ama
bir
yani
şey,
şey,
scheduler çok aptal
basit
bir şey.
hali.
Scheduler sadece bunu çalıştır diyor başka bir şey.
O zaman Shell çalıştırmayacak.
Shell'in ne yaptığını söyle. Shell sadece
Yok yani
exec
komutlardan
process
birisi.
denen, exec process denen bir tane system call çağırıyor. O kadar.
Ama mesela işte Shell'i çağırırsa birden fazla program çağırabiliyoruz. Yani
kendi
4
şey
tane.
mi?
Aynen.
Valla onu ben biraz önce uydurdum. Onu yapmasanız iyi olur.
Yapmayalım değil mi? Tamam,
Evet.
güzel.
Yapsanız güzel olur da. İkinci ödevde yapacaksınız.
Mantıklı
değil.
Şuraya yazdığım şeylerin hepsi çok unuttuğum şeylerdi ve kabul etti, hepsini yapacaksın. Şimdi bak. Bu benim dosyam. Show bunun altında adam Shell'da ben buna program adı verdim ya, o da o program adıyla Syscall atacak. O Syscall'da sadece işte create process.
Önce ben. Osman'dan önce ben şu işi halledeyim.
Evet ama mesela
Diyoruz bence ben.
bunlardan birisi bu Spim'in içinde çalıştırman lazım çünkü bunlar bir program. Senin konsolun içinde çalışmak lazım.
Şimdi moruk ne diyorduk? Şimdi az önce öyle Techical writing diyorduk. Evet. Abi şimdi ben biraz sakin ol.
Çalışan program bittiği zaman
Pardon. Bak harbiden kontrolü
ya da öyle olmaz.
bırak.
Öyle olmaz. Yani Shell çalışıyorken ama Syscall'da yok. Bizim o zaman Sleep Syscall'da. Normalde Shell çalışıyor. Create process yapıyor. Sonra process bitmesi
Ama yok daha çıkar.
onu da ekledim.
Komponent object mi oldu?
Yapmıyorsun. Hayır. Şöyle Shell'i çalıştırdın ya. Shell'i çalıştırdığında Shell create prosesi çağırdı. Create proses normalde bir prosesi yan anda create atıyor ama senden bağımsız olarak çalışıyor. Shell orada ne yapıyor? O prosesin bitmesini bekliyor. Ama bizde bekliyor diye. Bu Shell beklemiyor. Ama aynı anda ikisi de çalışamıyor.
Oraya yaklaştık. Daha geçiyorsun.
Shell bitmeyecek işte. Hocanın istemiyor. Yani komut isteyecek. ASM dosyası istemeyecek. Normalde adını verecek.
Galiba Vision da.
Yani mesela binary search diyeceksen binary search.
Ben de diyorum benim niye durduk yere exit'e sonra işte değil mi?
Komut olarak hangi
Artık bunun etkisi olarak ona gidip çok
Teknik öğrendiniz.
benim açımdan.
Gerçekten.
ben de istiyorum bir şey. Şaka maka yapıyoruz.
Dediği zaman teknolojide olduğunu sonra büyük prosesler nasıl prosesler onun adını bir sormak yok. Adını değiştirmedi. Bence yan prosesler. Bunu nasıl yapacağız? Ben bunu da yapabileceğim. Bir tane dosyası var. Onu al, onu çalıştır. Sonra online
Ben hazır olduğumda yapacağız değil mi?
Olmasını istediği şey bu. Vermemeyi çalışıyor. Bir tane sefer İstanbul'da diyor. Yolladığın zaman senin öyle yapacağın gece sorabilirsin. Yazdık. Aslında o kadar belli bir yere koyacak. Şen oraya bağlanacak. Orayı yaptıktan sonra tekrar kaldığı yere geliyor. Bana soracak. Hangi bir yere mouse'u kullanacağız? Hem oradan adres alacağız. Onu Eray'a yükleyeceğiz. Ama nasıl olacak? Uzun dosyanın sayfını göreceğiz. Bunu kim sistemlerinde? Hexadecimal çevirip memoriye atacaksın. Eray'la sağlayacaksınız. Ordu Hexadecimal kullanınca spinalize oluşturuyor. Ödevi yaptım ama yazacak adam var.
Dört tane assembly var.
Şeyde yazdım var. Şerden abi 25 numaralı şey var. Bir saniye. 25 numaralı sistem yanındayım. Sen 20 yap. Yani başka bir derste 20 yap. Diğerleri onlar yazdık. Gel başka bir şey. Sistem başlıyorsun. Dosyayı okuyorsun. O okuduğun assembly kodunu orada bir yere atıyorsun. Unlock'la yapabilirsin bunu. C'de. Unlock'la yapabilirsin. Eray'la anlattın mı oraya? Eray'la tutman lazım. Eray'la olacak, şeyin olduğu kaldığı yere geliyor. Amerika'da o ayrı bir tane içinde direkt şey hocam çarşamba günü gelip 2 dersi de aradan çıkartabiliyor.
Okay. So this is actually when the interrupt happens. Let's go back to this one. Interrupt happens. My process is put on the ready queue. Then after I handle the interrupt, somebody from the ready queue was taken back to the running. So this is the arrow number 2 and number 3. Of course, it always doesn't happen this way, but it's an example for number running to ready to running example, you could say. Okay, good. Let me move on. I showed you my process table, right? It say that 30% of the time your CPU is busy, 70% of the time your CPU, 70% of the time your CPU is idle, waiting for nothing. Well, that doesn't mean that I don't need to use the CPU. That means that I cannot use the CPU maybe. Why? Because no process is interested, or maybe some of the processes are waiting for something to happen, okay? Almost all of them are doing that. So let's do some calculations on it. Let's say if you are doing multi-programming, what is the purpose of multi-programming? If I keep more than one program, one process in my memory, if one of them is blocked, maybe I can run the other one, right? So that's the idea. So this way, I could use my CPU more efficiently. That was the idea, multi-programming. So what is the difference between multi-programming and time sharing? Time sharing, multi-programming, time sharing. This is a very classical question, actually. Sharing. Remember the first generation computers? In the first generation computers, we didn't have multi-programming, we didn't have time sharing, right? A person comes into the room, okay? He or she programs the computer using the switches, not any using the programming tool or assembly. After they run their program, they take the answer and they go away. So there is no multi-programming, there is no multi-sharing. With the second generation of computers, they said that CPU is so expensive. We cannot let a guy use this computer for 6 hours. It's so expensive. I mean, each hour is costing me like $6,000. So 10 hours, $60,000 a day. So that's a very expensive time. So what are we going to do? We are going to take lots of programs in the memory, and if one of them blocks, the others will continue, and that way, in a given amount of time, I will be handling more than one process. That was the idea of multi-programming. How about time sharing? What is time sharing? What is the difference between multi-programming and time sharing? Time sharing, I mean, as the name implies, it looks like something like multi-programming, and that's right. Without multi-programming, there is no time sharing, but there is an important difference between time sharing and multi-programming. That's the difference between the second generation computers and the third generation computers, yes?
Maybe in multi-programming, we are actually doing the same thing at the same time.
At the same time? There is only one processor. No way you can do the same thing at the same time.
There are no other processors.
No, single processor, yeah. Single processor, you are doing, well, I mean, don't take this time sharing as with the exact literal sense, okay? Time sharing is a term used by people to refer to something. It is not, we are sharing the CPU time one by one. That's already what the multi-programming is doing. But time sharing is a term that is used for something else, and we talked about it. You had an answer, didn't you raise your hand? You raised your hand, and you lowered your hand, but that doesn't matter. I didn't see your hand lowering. So, what's the answer?
Isn't multi-programming a paradigm more like programming knowledge? It's just a question of programming, like it can be processed, it can be switched at any time. Maybe.
That's what multi-programming says. As soon as I am blocked, I am going to switch to some other process.
Yeah.
So that's what multi-programming says.
And isn't time sharing the result of multi-programming?
Yeah, time sharing uses the multi-programming technique, but it is more than that. Yes.
Processes share the different resources.
What example?
Like printers or CPU or.
Well, I mean, multi-programming already shares the CPU among different processes, yes. That's what multi-programming does. How about time sharing? The first generation computers, yes. Many users use the same computer, just explain it a little bit more. That's it. I mean, with the multi-programming, you have the programs of many users at the same time, but time sharing is exactly like what you are saying, but there is important difference. Many users are using the same program, and they feel that they are the whole owner of the whole computer, right? They think that, what was the problem with the first generation computers? It was efficiency, right? You cannot let a single person use a computer for 6 straight hours. It's too expensive. So the person, why are they using it for 6 hours? Because they write their programs, they run it, an error occurs, they debug it, they run it again, like what we are doing nowadays, right? Until it is ready, okay? They said this is too inefficient, only one person is using it. So they made it multi-programming. You are submitting your job, like yourself, they take the jobs from 100 other people. So there are 100 programs running at the same. It looks like there are 100 programs running at the same time. Each one is doing something. As soon as one of them is blocked, the other one is running. Other one is running. So it takes maybe 6 hours to complete these 100 programs. So I am 100 times more efficient, right? I am 100 times more efficient with the second generation program, with the multi-programming. What is the problem with this approach for the operator, for the end user, for the programmer? Second generation computers, programmers didn't like them. They didn't like it. Do you know why? They liked the first generation computers better. I mean, the computer operators, of course, the owners of the computer universities, they were happy that using a single computer, they can now serve 100 people at the same time. But people didn't like second generation computers, the programmers, the end users. Why? Do you remember how you submit your job to a second generation computer? What? No, before the tape. Tape is done by the operator of the computer system. Before the tape, you had what? Punch card. You type all of your program to a punch card. You hand over to the operator. Operator takes it and loads it to a tape, right? And 100 programs on a tape is taken to the mainframe computer and it is run. So how many hours do you have to wait to get your answer? 6 hours. Why? Because it takes 6 hours to complete all of that programs, 100 of them. Before that, you don't get any answers. So if you have a single mistake, 6 hours means that the next day, you are going to do the same thing next day, another mistake next day. So at the beginning, for a first generation computer, all it takes me 6 hours to complete my job. Now it's going to take 3 or 4 days because every time I make a mistake, I need to change something. I need to resubmit my job, and it's going to take at least a few hours. So they invented time sharing. They say that let's give each user a terminal. Okay, what did the terminals look like in 1963? I showed you the video, right? Typewriters. Just it's like in Turkish daktilo, right? Typewriters. That was a terminal. So you type your program with a typewriter, and you get your answer on your typewriter printer out, and that was your terminal. With a time-sharing system, of course, it is multi-programming, but it looks to you as a programmer, as an end user, you own the whole computer. So back to first-generation computers, it takes you a total of 6 hours to start from the beginning. You write your program, you get your results, you debug it, and you find it, and you get your final result. In a single day, everything is okay with you. So it is both efficient for the CPU, for the whole computer, and it is efficient for the end user. That's the difference between the first generation and second generation and third generation computers. And nowadays we are using the third generation computers actually. I mean, the ideas are the same. We are both using multi-programming and time sharing. Okay, so with the time sharing, of course, there is CPU, and CPU sometimes is available, sometimes not. If a process is blocked, I have to wait for it. Let's try to model this. Let's say a process spends P% of its time waiting for I/O to complete. Let's say this is my process, this is time. Okay, I am using CPU, then I wait, and I use CPU, then I wait. So it looks like okay, P% of my time is spent while I am waiting. I am not doing anything. I am waiting. Because why should I be waiting? Maybe I am waiting for user to give me something, or I am waiting for network to load me something, okay? So fraction of time is P% of time I am waiting for the IoT complete, okay? So that means that, let's say, if my P is 0.1, or if my P is, let's say, 0.5, okay? That means that 50% of the time, if I have a single process in my computer, 50% of the time my CPU is idle, right? So what is my usage of the CPU? It is 1 minus P. So if, let's say, this is 4, if 40% of the time I am waiting for I/O, then 1 minus P is 0.6. Okay, I am using my computer 60% of the time. My CPU utilization is 60%, and I like to push this up. How would I do that? Let's use more than one process. Let's use more than one process. And process number 1 waits 40% of time for the I/O. Process number 2 is waiting again 40% of the time for the I/O too. If one of them is waiting for the I/O, the other one might be running, right? So that's efficiency. But there is a chance that both of them are waiting for the I/O. What is the chance of that both of them are waiting for the I/O? What? 20? If there is a 40% chance for this one, and there is a 40% chance for this one, what are the probabilities that both of them are waiting for the I/O at the same time? 40 times 40, right? It's like 0.4 times 0.4. It is 0.16, right? So it looks like 1 minus 0.16 is, okay. 1 minus 0.16 is 84% utilization. So I come from 60% utilization to 84% utilization. So by using more than one program at the same time with this approach, I can get this, right? That's the model. So let's extend it even further. Let's say I have n processes. Okay, maybe this is too big. Let me make this a little bit smaller and put it up there. Okay. So I said that 80. So if I have two processes, it is 84%. Let's say you have n processes, and each one is 0.4. So if I have n processes, if n of them are waiting at the same time for the I/O, then my CPU will stay idle. That means that P to the power n percent of the time, my CPU will sit idle. Okay? And if I take 1 minus P to the power n, that will give me my CPU utilization. Okay? That will give me my CPU utilization. So this is a very simple model to calculate your CPU utilization formula. That doesn't mean that always make your utilization calculation this way. It's a very simplistic approach. Where I assume that each process has the same I/O wait periods, which is not realistic, right? I assume that one just to make the things simpler a little bit. But this would be the formula. I think this is what I get from CPU utilization 1 minus P to the power n. So this formula, of course, it depends on the value of P. I said that my P is 0.4. The book did some experiments like this one. Let's say the book said that if P is 0.8, and if I have 10 processes, that means that I have almost 90% CPU utilization. If I/O wait time is 80%, right? So 10 processes at the same time still cannot use 100% of my CPU. But 100% CPU utilization is not a very good thing. You want to keep some slack, a fraction of CPU. So that's what it is. But if your job is like 20% I/O wait, then even if you have two processes, that will keep your busy. That will keep your CPU busy for a much larger fraction, right? So these three things. This is 80% I/O wait, 20% I/O wait, 50% I/O wait. You can draw these kind of curves to see what's happening, to analyze what's happening with your operating system. Of course, you want to stay. You don't want to have utilization around 20%. 100% utilization is not good because this is a model, right? It's an approximation. If you are heading for 100%, if you have one more process, that's going to be good, not good. So maybe 80% CPU utilization is good if you have a mainframe. So that means that if you are aiming for 80% CPU utilization, depending on your process characteristics, sometimes you can support 7 processes, sometimes you could do 3, sometimes you could do just 1. Okay, so very simple model for multi-programming. Think about this. If you have more than one processor, how would this change? If you have more than one processor, if you have more than one processor, and let's say if you have more than one processor, if a single process, that means that one of your processor will stay idle all the time. If you have two processors, and if each of your, if you have two processors and two processes, then for the 40%, it looks like 60% of your CPUs will stay idle, right? So doing this with the multiprocessor is more complicated than this, but you can figure out something. Okay, good. I think there was a good example with the book. Okay, let's look at this one. Another one. Let's say my computer has 8 gigabytes of memory. Good. My operating system takes 2 gigabytes of memory size. Okay, and each user program takes 2 gigabytes. Let's go back here. Okay, let's try to. I think I need to sit down. Okay, this is my, and I need my glasses. My glasses are, where are my glasses? What? Where? In front of me. Okay. This is my memory. It is 8 gigabytes. OS is here. OS is here. It is 2. And I have 3 processes. Each is 2, 2, and 2. The whole memory is occupied. I cannot add one more. Okay, I cannot add one more. So it says that my I/O wait time is 60%, 80%. That means that with the 3, I could get, right? I could get how much? 50%? 50%, right? 50% utilization. I cannot do better than this. I mean, my memory is that I cannot add more. I cannot add more processes because all of my memory is occupied. The idea is let's add more memory. Okay, let's add 8 more megabytes of memory. Let's add 8 more megabytes of memory. So my system is going to look like this. OS is here. OS, for some reason I say 8. Okay, OS is here. And with 8 more, I have 16 megabytes, right? I have 16, it's gigabytes, okay, it's megabytes, gigabyte doesn't matter in this case. 16 gigabytes of memory. OS takes 2 gigabytes. Now I have 14. That means that I can fit 7, okay, 7 processes. 1, 2, 3, 4, 5, 6, and 7. That means that I can do this now, okay. How? It is around, what? It is around 80%. So I went from 50% to 80% by adding 8 more megabytes of memory. Sometimes people would say that, okay, my computer is too slow, so what did you do? I added more memory. Adding memory means that I can do multi-programming even more. If you add more memory, that means that you can keep more processes in your memory, and switching between them is much faster now, and your computer will be faster. So, I mean, memory has nothing to do with the CPU speed much, okay? But if you add more memory, that means that you can run more than one program, more than 4 programs, 5 programs. You can seemingly run at the same time, and that will make your overall system more efficient. So it works nice. Let's add 8 more megabytes of memory. So let's say I have, so this is the case for 8 gigabytes. This is 16 gigabytes. Let's make it 24. So with the 24 megabytes, how many processes can I run? 24 megabytes. 22 and 11. I can write 11, right? 11. So 11 in this thing is how much? 10 is 90%, right? 11 is maybe 95%. So with the, this is maybe 95%. Again, 8 gigabyte more memory here. 8 gigabytes of more memory and 8 gigabytes of more memory. The effect is not same. Okay, I mean, this is a 30% increase from 50% to 80%, like half of the whole performance comes from 8 megabytes. Now it is like just 15%, not good. Okay, so the second 8 gigabytes did not work very well because, I mean, my idle time is not that big anymore. So maybe you can make a decision by looking at these numbers. How much is a gigabyte of memory? Okay, how much is a gigabyte of memory? Would I spend that kind of money for a 15% CPU utilization increase? Can I do that? So it's a very good mathematical way, analytical way of making this decision. Should I buy more memory to my system, or this kind of CPU utilization is good enough for me? Okay, it doesn't look like, if I look at this picture, it says that I am using 25% of my CPU. It doesn't look like if I add 8 more gigabytes of memory. I think I have 8 gigabytes of memory, I think so. If I add 8 gigabytes of memory, it doesn't look like my CPU utilization will increase because it is already 80% idle. And by the way, I'm like loading this up because I am saving all of these videos. It takes lots of CPU power. Yeah. So I think I'm happy with my computer. Are you happy with your computers? If you're not, then try adding some memory. But do this calculation first, okay? When you are loaded, okay, when you think that your computer is slow, just look at this number, okay? If that number is close to 80%, maybe adding more memory will help you. Okay? Make that calculation yourself. Good, any questions? Again, these are oversimplifications because, I mean, as I said, I have, how many processes did I have? I had 100 processes, right? And all of them, they do not show this characteristic of 80% I/O wait time. Okay, most of them are waiting something to happen. Most of them are maybe 99% idle. They are waiting something to happen. Okay, so 99% of the time they are waiting something to happen. So adding more memory probably will not do much because I have enough idle time. Okay, good. By the way, these processes are ready processes, right? I mean, we are not talking about the block processes. If the processes are blocked, doesn't matter how much memory you add, they have to wait for something to happen. Okay, we are talking about the ready processes, and the ready processes, as you have seen, is not much on my computer. Good. Any questions? Okay, let's talk about. Oh, okay, I think it is the same thing. 80% average wait time. It is about 50%. When I add 8 more gigabytes of memory, it is like 80%. In other words, additional 8 gigabytes bought me 30% increase. If I add 8 more gigabytes, it's like maybe 95%, which is not that much. Okay, so let's go back, and let's talk about process switching. As I said before, switching from process number 0 to process number 1 has to be done by the operating system. Process number 0 either has to say, I am making a system call. Operating system takes over. Okay, I will handle this call, but I will suspend you. Okay, I will put you in blocked list, I will put you in ready list, but I will let some other process run. So before I make this switch from 0 to 1, operating system has to work, either interrupt handling or system call handling, whatever. Okay. So what is the cost of switching from 0 to 1? You need to save lots of registers. You have seen those, right? And you need to load lots of registers from the other process. Two things: save lots of them, load lots of them. And in fact, when you are doing some kind of operating system job, you need to call some of your functions, and those functions, they have to remember some of the data that they had used. They have some loading time too. We did not talk about this, but there is this virtual memory concept of page tables. Page tables. Okay. Or TLB buffers. Okay. These are used for virtual memory concepts, and they are very large tables. Each process has its own table. Okay. And they are managed by the operating system. If you switch from one process to another process, these all tables, they all have to be reloaded. Okay. They all have to be flushed and reloaded again. It is expensive. That's why we call this a context switch. Context switch. Okay. Context switch is expensive. Especially it is very expensive for recent CPUs, because recent CPUs, they have very large page tables, very large TLBs, they have very large cache sizes. If you switch from one process to another process, your cache will be invalidated and you have to repopulate your cache again. Okay, those are very expensive stuff. If everything is loaded, all the page tables are ready, your cache is ready, all the pipeline is filled, okay, so everything is very, very fast. But if you switch from one process to another process, think about pipelining. What happens to your pipelining if you just jump to some other location in your memory, right? I mean, if the pipelining is very, very high level, at the advanced level, like the superscalar pipelining, you will get a very bad hit in terms of performance. So switching, especially for the recent processes, is expensive. Context switch is expensive. Why? Because I am doing this and this and this. That's why scheduler has to be very careful, and that's why I need to keep the switching. I need to keep the switching test, the thing at a very low level, at a minimum. Okay, don't switch too often. That's one of the things. So we are going to look at it later. But that's one of my concerns. So people have seen this. Okay, if you switch from one process to another process, you have to update your page tables because you are changing your memory, right? You are not looking at this memory anymore. You have to look at the other parts of memory. They said that, okay, I mean, if I didn't have any multi-programming, then context switch would not be a problem because I don't have a multi-programming problem anymore. Context switch doesn't happen, and I don't get that hit. But multi-programming is useful even in a single program, even if a single process. I may prefer to use multi-programming because when I say, okay, while this happens, while I am waiting for this, I will do this. While I am waiting for this, I will do other thing. In a given process, I may prefer to use multi-programming. So they put all of them together. They say that maybe switching process to process is too expensive. Maybe we can invent something different. Let's invent anything called thread. Okay, thread. Okay. Thread is very similar to a process. Okay. So that means that like the processes, threads run in parallel. Okay. They look like they are in parallel. That's the common part. You can run many threads at the same time. But unlike the processes, they share lots of stuff. Okay. 2 or 3 threads running in the, let's say, this is my process. Inside my process, this is my data segment. Okay. And other than that, there are open files. there are system-related structures. Within a same process, I may run more than one program. Each one is a thread. Okay. Each one is an execution. Each one is an execution. Each one has its own program counter, stack pointer. Okay. And some of the registers, but each one is sharing the same memory area. So switching from this thread to this thread is still expensive, but it is not expensive as switching from this process to this process. And inside this process, I have other threads. Okay? So they say that if you're going to do multi-programming in your program, in your system, prefer threads instead of doing multi-processing. Of course, if I have two different users, each user should have their own processes because there is this information security problem. I cannot let other people see my data. But if I am a single user and the program that I write, okay, needs multi-programming, more than one execution happening at the same time, use the threads. And the difference between the threads and processes, threads share lots of stuff. They share the same address space and other data. Using this idea, okay, we get lighter threads, and they are very, very fast. Sometimes they are as fast as 100 times. Okay, so 10 to 100 times boost up rates is not very uncommon with the threads because they are saving a lot of time due to overheads of this context switching. Okay, so threads are other ways of achieving this multi-programming, but they are restricted. Why are they restricted? Because if you are doing something multi-threaded in your program, it has to be in the same program. Different users cannot see each other's data. So for different users or different programs should have their own processes. But within the same program, I could do multi-programming, and multi-programming can be done using the threads. Okay, these two things are important. I mean, multi-threading doesn't come without any trade-offs. Okay, because there is no protection between the threads because we said they share data. Okay, they share data and address space. Okay, so there is no protection between the threads. This thread can see whatever this thread can see. This thread can modify whatever this thread can modify. Okay, this didn't happen between the processes, but between the threads, yes, it could happen. Of course, this thread and this thread cannot share the same thing. These are the threads of different processes, right? But these two, they share lots of stuff. That's why there is no protection between them. You don't have to protect the data from one thread to the other thread, which makes the things faster, a lot faster. Okay, and by the way, if you have more than one process, each process competes to get more CPU resources. Each process says that they think that I am the owner of the whole computer. I have all the memory space. I have all the disk access, and I like to do my things in a very, very efficient and fast way. Use CPU as much as possible. So there is competition between the processes, but between the threads there is cooperation. Threads know that other than me, there are three other threads, and we are cooperating. We are trying to achieve something all together, and I need to help them, and they are going to help me. Why? Because all four of them are written by the same programmer. They are the part of the same design. Okay, so these are the differences between threads and processes. This is a very classic example. This is a process, a home with its own door, entrance door, and the windows, and the chimney, and the road, and etc. This is like a process. And if I like to make another process, let me sit down a little bit. If I like to make another process, as I said, this is a very classical example. All I need to do is just call fork. What does fork do? Fork takes this nice house and duplicate it, same thing, yeah, it is here, and duplicate it maybe, and here. So if this one costs 100,000 Turkish liras, this one will cost the same and this one will cost the same. Why? Because building such a home is expensive. You need to build the road and you need to buy this expensive door and chimney and etc. and power lines and etc. They say that each one is a process. How about the threads? Threads are like this. Threads are one large apartment, one entrance, and I have, okay, this is process 1, process 2, and process 3. So they share the same chimney, they share the same door. They have, of course, they have their own windows, right? They have their own windows. Okay, this is thread number 1, thread 2, thread 3, and thread 4. And the road to the apartment is shared by all of them. So they are kind of sharing the infrastructure of the whole apartment. Which one would you like? I like this one better, but this is expensive. Right? This is expensive. If there is a problem with your roof, you have to fix it yourself. If there is a problem with the roof here, all 4 of them are responsible for fixing it. Okay. If there is a problem with the road, all 4 of them are responsible. Okay. Why? Because they are gonna come together and they will pay for the road repair. This is safer. Okay. You know that if your neighbor does a bad thing, you are not going to get affected from it. But if your neighbor doing a bad thing, like making lots of noise, or they are demolishing their columns or whatever, they are breaking the columns, that's not going to be a good thing. And the thing is that they can know what kind of meal you are cooking, right, by just smelling the air. So that's not a good privacy thing, right? I mean, everybody knows what kind of thing you are eating, but with this approach, you don't have it. So these are the processes expensive. If you don't trust your neighbors, do this. But if your neighbors are good enough, maybe this is much better because this is sharing lots of stuff. Sharing lots of stuff. You don't have to spend lots of money for cooling your house or making it warm during the winters, right? This is just an analogy. Our book doesn't use it, but the others use it. So these are the threads, these are the processes. Sometimes we like this, sometimes we like this. That doesn't mean that this is always better than this. This one is always better than that. There are ups and downs, and we are going to see. Sometimes I will definitely need to do these because this cannot be a operating system thread and this a user thread. It cannot because both of them cannot share the same thing. But with the processes, this could be an operating system process house, and this would be a user house because they are completely different. Okay, any questions so far? Yes.
Who makes the switch between threads?
Well, that's a very good question, and I need maybe 4 or 5 slides to tell you what to do. If the thread is supported directly by the kernel, if the kernel knows that there are multi-threading happening in your process, it is the job of the kernel to do the thread switching, okay? But if the kernel doesn't know that you are running threads in your process, it is your process's responsibility. One of them is called user threads, the other one is called kernel threads, okay? And they have advantages, ups and downs. Usually, we don't prefer to one over the other. We kind of use a hybrid approach. Okay, any other questions? Okay, threads are used much more often than the processes, but that doesn't mean that I don't use the processes. I use the processes a lot. Good. Okay, that's it for today then. We will continue next week on Monday.